Today, we're going to pull back the curtain on one of the most fundamental forces in our universe. It's something totally invisible, yet it powers pretty much our entire modern world. We're talking about electromagnetic waves. So let's just jump right in with a question. What's the connection between sunlight, the Wi-Fi signal you're probably using right now, and a medical X-ray? I mean, on the surface, they seem like they couldn't be more different, right?
Well, it turns out they're all part of the same incredible family. They belong to this invisible world that is buzzing all around us and even through us at every single moment. And this world, well, it's the foundation of almost all of our technology.
So let's explore this invisible world. And to really get it, we actually have to take a trip back in time to a point where two of nature's biggest forces were seen as complete strangers to each other.
You know, for most of human history, scientists looked at electricity and magnetism as two totally separate things. You had lightning strikes, and you had compasses pointing north. One was about static shocks and currents, the other was about magnets. Nobody really thought they were, two sides of the same coin.
And then this guy comes along, James Clerk Maxwell, a Scottish physicist. And he didn't just have a hunch, he had the math to prove the connection. He basically said, look, I think I found a secret key, a key that's going to unlock the very warehouse of nature.
And that brings us to what I like to call Maxwell's prophecy. Because what he did was so much more than just connect a few dots. His work actually predicted the existence of something that would completely change the world.
Okay, now don't let all the symbols on this slide scare you. We're not solving anything here. Think of these four equations as the basic rulebook for electricity and magnetism. And what Maxwell realized was amazing. Look at the last two. A changing magnetic field creates an electric field, and a changing electric field creates a magnetic one. They create each other, kind of leapfrogging through space. And when he calculated how fast this thing would travel, it was the exact speed of light. It was this incredible jaw-dropping moment in science. Light is an electromagnetic wave.
So, what is an electromagnetic wave really? Well, it's this beautiful, self-sustaining dance. You've got an electric field and a magnetic field, and they're constantly creating each other as they move through space. They wiggle at right angles to each other, and both of them are at a right angle to the direction the wave is actually going. It's a traveling, three-dimensional wave of pure energy.
And these waves are just weird. First, they all travel at the speed of light, the ultimate speed limit in the universe. And here's the really strange part. Unlike sound waves or waves in water, they don't need anything to travel through. They're perfectly happy zipping through the total vacuum of empty space. That's why we can see stars that are millions of light years away. Oh, and of course, they carry energy. That's how the warmth of the sun gets all the way to Earth.
But here's where it gets even cooler. Maxwell's discovery wasn't just about the light we can see. It blew the doors open, revealing that visible light is just one tiny piece of a gigantic, invisible family of waves.
And this is a really humbling idea when you think about it. Every single color, every sunset, every work of art, everything humanity has ever seen with its own eyes, it all exists in this impossibly narrow little band of a much, much bigger reality, the electromagnetic spectrum. And here it is, the whole family photo. Let's take a walk through it. Down at the long wavelength end, you have radio waves, which bring music to your car. A little shorter, and you get microwaves, which, heat your food, but also give you Wi-Fi. Then you've got infrared, which is basically heat radiation. It's what night vision goggles see. And then bam, there's that tiny slice of visible light. After that, the energy starts to ramp up. You get ultraviolet or UV light from the sun. Then the really high energy stuff, X-rays, which let us see inside our bodies. And all the way at the top, gamma rays. They're all the exact same thing, just waves of electricity and magnetism. The only difference is their wavelength.
Okay, so this is all really fascinating, but why does it matter to you? Well, because humans have figured out how to use nearly every single part of this spectrum to build our entire technological society. Let's bring this right into your kitchen.
So the humble microwave oven. It's a perfect example. Inside, a little device called a magnetron shoots out microwaves. Now these waves are tuned to the perfect frequency to make water molecules, which are in almost all food, vibrate like crazy. As you can see here, they just start spinning back and forth billions of times a second. That creates friction between the molecules, and friction creates heat. And just like that, your food is cooked. It's not magic, it's pure physics.
Or think about radar. The name literally tells you what it does: radio detection and ranging. It's basically how we see things using radio waves. You send out a blast of radio waves, they fly out, hit something like an airplane, and bounce back. A receiver listens for that echo. And by timing how long it took for the echo to return, you can figure out exactly how far away that plane is, how fast it's going, and which direction it's headed. Pretty cool, huh?
So it seems pretty clear, right? Light, radio, X-rays, they're all waves. Case closed. But, well, just when we think we have the universe all figured out, physics loves to throw us a good curveball. So let me ask that again. Is light just a wave? Is that the whole story? As it turns out, the answer is no. And the truth is one of the weirdest and most mind-bending discoveries in all of science.
It seems that light has a split personality. Sometimes, as you can see on the left, it acts exactly like a wave. If you shine it through tiny slits, it creates interference patterns, just like ripples on a pond. But in other situations, it acts like a stream of tiny little bullets, these little packets of energy called photons. It can literally knock an electron off a piece of metal, something a wave shouldn't be able to do. So which is it? Is it a wave or is it a particle? The bizarre answer is, it's both, at the same time. What you see just depends on how you decide to measure it.
And that just leaves us with this final amazing question to think about. We started with something as simple as static electricity and magnets, and we ended up with this vast invisible spectrum that runs our world, only to find out that its true nature is something that almost defies common sense. It just makes you wonder, what other incredible secrets is our universe hiding from us right here in plain sight?